Well, hello. We're going to talk about probability. Probability is part over whole. Okay? Once you do that, you multiply by 100. And then you'll get the percent, whatever it is. Okay? This is talking about sample spaces. Basically, there's a bunch of outcomes that you can have. There's a person guessing on a test, and there's 4 questions. And C represents a correct answer and I represents an incorrect answer, okay? So if the person misses all 4 questions, I is for incorrect. So incorrect for the first one, the second one, third one, and fourth one, okay? So that one is the 0 number correct, okay? 1 correct could be, the first one could be correct, then the other 3 missed. Second one could be correct, the other 3 missed. The third one could be correct, and then the other 3 missed, and then the fourth one could be correct. So those are the outcomes that are going to be 1 correct out of 4. Okay, and as you can see, this is the one, there's 1, 2, 3, 4, 5, 6 cases where you get 2 correct. Okay, there's 1, 2, 3, 4 cases that you get 3 correct, and then to get all 4 of them right, of course, it'd be C, 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 and C to get 4 correct. Okay, so there's a certain number of outcomes here. Okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 16 outcomes, okay? And that's what's going to go on the bottom. That is your whole, okay? So you have to figure out the part that they're asking in the question. So we look at the question here, and it says the probability of a student guessing exactly 2 correct answers. Okay, we know there's 16 outcomes, and we look at the 2 correct answers. So there's 1 possibility, 2, 3, 4, 5, and 6. So 6 out of 16, then we multiply it by 100, and we get the percentage chance that they actually can do that. So 6 divided by 16 times 100 is going to be 37.5% chance to do that. Okay, so 37.5%. Okay, what is the probability of the student guessing all of the correct answers? Okay, so you know 16 is on bottom because there's 16 outcomes. Okay, so to get them all correct, there's only one way that they can do it. Okay, so you put 1 over 16 times 100, and then we do the calculation. So let's clear it. 1 divided by 16 times 100 is 6.25% chance to get it right. Okay, very low chance of guessing all 4 correct. Okay, so here we're going to talk about probability of an event. Okay, compliments was when you nod it. Okay, if you have 3 marbles out of 10, then whenever you nod it, it would be 7 marbles because that's how many are left. I'll show you on this one right here. See where it says not? Okay, but first let's do this one. Okay, we've got a spinner with 5 numbers on it. Okay, so you've got this spinner that has 5 numbers on it. 1, 2, 3, 4, and 5. Okay, so if you spin it, what's the chance of getting a 4? Well, there's only 1 4 on there, right? And there's 5 numbers. So 1 out of 5 times 100. Anyway, that's 20%. Okay, I'm not going to punch it in. Okay, here, not getting a 4. Okay, there's 1 4, so the rest of the numbers would be not a 4. So 5, 1, 2, and 3. So there's 4 out of 5 chance here. Okay, so times 100, if I punch it in, I would get 80%. Okay, an 80% chance to get 4 out of 5. All right, so probability of getting a number less than 3. How many numbers on here are less than 3? Well, the 2 and the 1. So there's a 2 in 5 chance of getting a number that's less than 3. Okay, so 2 out of 5 times 100 is equal to 40%. Okay, and then this is kind of weird sounding, but a probability of getting a number not less than 3. So 3 is good, and 4 is good, and 5 is good. Okay, not less than 3, well, that's a 3, a 4, and a 5. So 3 out of 5. So 3 out of 5 times 100 is equal to 60%. Okay, I'm only going to show you one of these. This is the only kind I'm going to show you. The probability that your dart lands in the shaded region. Okay, so the whole thing is 12 times 12, right? So the area of the square is 12 times 12, and that one is 144. Okay, now the circle has to disappear because we're talking about this landing here on one of these parts here. So it's going to be a very small percentage to be able to hit that part. Okay, so we need to subtract the circle away. Okay, so the area of the circle. Now, if you remember, area of a circle is pi r squared. It's on the formula chart. Okay, so r would be the radius. Okay, the diameter would be 12. All the way up here would be 12, but the radius would be 6, right? So I'm trying to get the area of this so I can subtract it away, and the only thing that would be left would be this little part that's around the edges. Okay, the shaded region. Okay, so pi r squared. So I'm going to put pi 5 squared. Okay, and how you would do that? Whoops. How you would do that with a calculator is you can see that button right there, right above the caret key. There's a pi. So you go second, and then you hit this, and you got pi up there, right? Okay, and then I put the 6 and square and hit enter, and that gives me 113.1. Okay, so 113.1 is the area of the circle. Okay, so I'm going to subtract this away so that the only thing that is left is the shaded part. Okay, so I add that up. See, 144 minus 113.1 is 30.9. Okay, so 30.9 is the shaded part. Okay, the shaded area, the part around the edges. So now I'm doing probability part over whole. The whole, of course, is the whole square, which is 144 in area. And then the shaded part that we're looking for is 30.9. So we times that by 100, and that's equal to something. Okay, 30.9 divided by 30.9 divided by 144 times 100 is 21.5. Okay, so 21.5%, okay, is that is the percentage chance of throwing a dart and hitting the outside part, the shaded part. Okay. Now, what is the percentage chance of having your dart landing inside the circle? Be much bigger, right? Okay. So my probability will still have the 144 on bottom, but we want the area of the circle on top. Okay, and we found that already. It was 113.1. 113.1 divided by 144 times 100 would be 78.5. Okay, so times 100, that would be 78.5, which, if you look at it, this one and this one add up to 100, right? So I could have just said 100 minus this to get that. But this is the percentage chance of you landing a dart in the middle, in the circle. Okay? Very good. All right. Next page. Here, I'm not going to do these two. Okay? Now we're going to go to this. Okay, so this is a table of pizza. Okay? People at parents at a party were selling pizza or giving out pizza. And there was a thin crust, 34 of them were pepperoni, 36 were plain cheese. Thick crust, 8 of them were pepperoni, 12 of them were plain cheese. Okay, this asks, what is the probability that a student chooses a thin crust with pepperoni? Okay, thin crust and pepperoni would be this guy. Okay, so 34. So that would be on top. We're doing percentage, right? Okay, so they want to know what kind of pizza, all the different types of pizza that somebody would select. So we have to add all these up. 34 and 36 is 70. 8 and 12 is 20. So 70 and 20 is 90. So 90 is the total. Okay? So 90 will get put under here, and then you'll times by 100, and you'll know your percentage of the people that would get a thin crust pepperoni pizza. Okay? So 34 divided by 90 times 100 is 37.8%. Okay? 37.8%. All right, so what is the probability a student does not, there's that not word, okay, does not pick a thick crust plain cheese, so that one. But they said not, so not 12, so everything else, right? So 90 minus 12 is 78, right? 90 minus 12 is 78. That's all the other ones, these three parts, that are not this 12, okay? So 78 is the one that goes on top over 90 times by 100, and you would get, let me see, 78 divided by 90 times 100 is 86.7% chance to get all of these three types. Okay? All right. Down here, a spinner has 5 sections. Okay, we want to understand the difference between experimental probability and theoretical. Theoretical is theory. You flip a coin, you're going to get a 0.5 chance, right? Because it's 1 out of 2 to get a head, right? 1 out of 2 chance to get a tail. That's theoretical, okay? But in practice, when you experiment, if you flipped a coin 100 times, you might not get 50. You might get 60 heads, okay? So same here. This is when we did the experiment. We did an experiment and 5 reds came up, 20 greens came up, 3 blues, 10 yellows, and 12 purples when we were doing a spinner. And if you add those up, that's 50. Okay, there's 50 spins. Okay, so what is the experimental probability of stopping on each color? Okay, so red was 5 out of 50, right? So I'm just going to put R was 5 out of 50. And then you times that by 100. Okay, I could bump that up, and I know that that would be, let me see. Yeah, it'd be 10%. Okay, and then green was 20 out of 50. Okay, we bumped that up, both of them by 2 to get 100 down here. I mean, you could say that times 100 and get it every time, but I'm just doing it my way. 40% because these are easy ones. Okay. And then the blue, make sure I have room down here. Okay, blue was 3 out of 50. If I bump them up both by 2, then it would be 6%. Okay. Yellow was 10 out of 50. Okay, 10 out of 50 times 100, okay, is going to be 20%. Okay. And then the last one, purple, would be 12 out of 50. Which is, let me see, that'd be 24%, okay? All right. So the theoretical probability of stopping on a color. Like to get a red, there's 5 colors, and if I get a red, isn't that 1/5? Isn't that true for all the colors? Like the chance to get a green is 1/5, the blue is 1/5, the yellow is 1/5, the purple is 1/5, okay? Times 100, that's 20%, right? Okay, so down here it says which color is the experimental probability and the theoretical probability where they're the same, okay? Which ones are the same? We know that theoretical is 20%, and if we look at all these, we find another one that has 20%, so that's yellow. So yellow actually worked out exactly according to theory, okay? Next. Okay, so if you're trying to get a code, a password, okay, say the password would be YOU, and these are the only letters that you could use, only 6 letters, okay, there's 6 letters total, okay, all right, so let me show you how it works. They're a combination, you can multiply them together, okay, so to get a Y, it could be any one of the 6 colors, right, okay, I mean not colors, but letters, okay, so 1/6, okay. Now it says that letters can be used more than once. In other words, I could use every letter every time. Okay, sometimes they say, like on this problem, they're going to say, okay, once you use a letter, then you can't use that letter anymore. But this one you can. Okay, so to get an O, it would be 1/6. And then to get a U, it would be 1/6. Okay, so if you multiply those all together, 1 divided by 6 times 1 divided by 6 times 1 divided by 6 times 100 is 0.46. So it's less than 1%. Okay, so a 0.46% chance of getting that correct if you guessed those 3 letters. Okay, anyway, so it's hard to guess. Think of it if it had the whole alphabet and numbers and whatever else. So it'd be really hard. Okay, so this one, the letters cannot be used more than once, okay? They can't be used more than once. So this time we're trying for AIE, okay? So that's this letter, and that letter, okay? So on the first one, it's normal, okay? The first one, it's normal. We're trying to get an A, so that's a 1 in 6 chance, okay? Now, Once I get to A, then it's gone. It does not count. Okay, so if I want to try to get another one, it would be a 1 in 5 chance because A is gone. Okay, now the I, after I do this, I is gone. Okay, so the last one's 1/4 chance, right? And let me punch that in. 1 divided by 6 times 1 divided by 6 times, no, I did it wrong. Okay, 5 there. Okay, times 1 divided by 4 times 100, and you get a 0.83 chance. Okay, still less than 1%, but a better shot at it at guessing the password. Okay, because they don't have as many letters because we had to cancel a couple of them. Okay, so this is a better password. Okay, better password. This is the worst password of the two. Okay, so this one is an independent action. Okay, independent means that nothing changed as you went along. They didn't change. The letters didn't change. It was always the same set of letters. Here, something changed. We got rid of one, and my number of letters each time was different. So this is a dependent type of problem. Okay, dependent. If you did a spinner and then you rolled a die and tried to find the probability, that would be independent. Okay, because neither one of them messed with each other. But if I had a bag of marbles and I took one of them out and I put it over here to the side, all of a sudden the bag of marbles had less marbles. So that's dependent because now the new bag of marbles, or the same bag basically, has less marbles. So that's a dependent. So it depends on how many's in there now. Okay, so that's dependent. All right, so I'll show you this one and we'll move on to the next page. All right, so collegiate soccer, male, female. Collegiate basketball, male, female. All right. You randomly select a soccer player that's female. Okay, soccer player. Okay, soccer's here and female's here, so that's this one, right? So that goes on top, 36,523. And then do I add up all four, or do I just do soccer players? Okay, this talks about soccer players, so these are the only two that you need, so you add both of those up. You say 36,523 plus 37,240. Enter, you get 73,763. Oops, that's a 3 times 100. Okay, so 36,523 divided by 73,763 times 100. Okay, that's a 49.5% chance that you're going to get that combination of a soccer player that's female. Okay, so we'll have the percent sign here. Okay, then this last one says that we want a male student that's a basketball player. Okay, so a male student right here would be this one, and a basketball player. So would I do these two? The only qualifier was male student in the beginning. So the first one said male student. So these are the two that have male students in it. So we want basketball instead of soccer. So these two we would add up, okay, to be the total, the male students in general. So we say 37,240 plus 31,863. Hit enter. That's 69,103. That's what's going to go on bottom here, 69,103. And then on top, you're going to have this 31,863, and then times 100. Okay, so 31,863 divided by 69,103 times 100. Okay, and you get 46.1%. Okay, that's the chance of getting a male student that's a basketball player in this situation. Okay, not doing this one. Okay, moving on. All right, we're almost done. Okay, so on this one, all right, independent and dependent. We talked about that for a minute, and we also are talking about doing a combination probability, okay? So, let's see, was there another one? Yeah, that's it. Okay, so on this one right here, the probability of A and B, anytime you have and, that means to multiply. So this is like a multiplication of the two events, okay? I don't like this one very much, so I'm not going to talk about this. All right, so look here. If you have a spinner, okay, what is the probability that you get a 5? Okay, so that you get a 5. The first event is a 5. Probability, wait, let's put P. Probability of a 5, and then the second time, a number greater than 3. I'll say number greater than 3 or something, okay? So 5 is just, that's 1 out of 8, right? So that's a 1 in 8 chance, and then we're going to multiply, okay? And then the second one says we need a number bigger than 3. Okay, what's bigger than 3? 4, 5, 6, 7, and 8. So that's 5 out of 8 that's bigger, okay? So we take these, multiply, and times 100, and we have our percent chance of getting that. So 1 divided by 8 times 5 divided by 8 times 100, okay? So that's 7.825%, or 7.8% is what we'll say. Okay, that's to get a 5 on the first roll, and then 3 or bigger. Okay, all right. So let's look at this. Okay, that was an independent event because 2 spins on the spinner, nothing disappeared. There's always 8 numbers on the spinner, nothing changed. Okay, now here's a dependent event because you've got a pile of money. You got 20 $1 bills and you got 5 100s. So a bunch of a bunch of $1 bills and 5 100s, okay? The first event is to get a $100 bill, okay? The second event is also to get 100, okay? So down here, when we work the problem, we would say that the first event is to get 100 out of 25 bills, right? Isn't there a 25 bill pile? Yeah, there's 25 bills, okay? 5 of them are hundreds and 20 of them are single dollar bills. All right, so they said, what's the chance of getting 100? Well, there's 5 of them. So 5 out of what's the total? Well, 25. Okay, so there's 5 and 25 chance. Now, if you randomly draw a bill from the bag and set it aside, here's the key. That makes it a dependent event. That means that we're not going to have one of the bills anymore. It's going to be gone. We put 100 over here somewhere. Okay, there's a $100 bill sitting over here somewhere. Okay, we moved it out. Now there's, to get a $100 bill on the second event, there's only 24 bills left. And how many hundreds are there? Well, there was 5, now there's 4, okay? So this depended on whether or not we had to replace it or not. They use the word replace it. Here they say set it aside. So we did not replace it. We didn't put it back in the pile, okay? So now you multiply this times 100 and you get your percentage chance to get 100 and then get another 100 out of this pile, okay? Without replacing this. We put it off to the side, okay? So let's do 5 divided by 25 times 4 divided by 24 times 100, okay? And we got it. That's a 3.3% chance of pulling 100 and then pulling another 100 if we left 100 out that we first got. Okay? All right. Well, have a good one.